So, now we will demonstrate how to measure the measure the focal length of a concave mirror lens. So, in last class I have demonstrated how to measure the focal length of a convex lens, now concave lens. So, again this procedure is similar of convex mirror. Okay. So, in convex mirrors, as we have discussed that only you can see the virtual image, okay, and erect image. In case of concave lens also, we can see only virtual image. Okay. So, directly we cannot measure the image distance. Okay. So, we have to indirectly we have to measure. So, we have to take help of convex lens, as we took help of convex lens in case of convex mirror, right. So, this here also this similar procedure as we have discussed for convex mirror. So, here, so in last class we have measured the focal length of a convex lens, right. So, this is a object needle. So, then we found the say this is not there. So, this convex concave lens is not there. So, this we found the image position, okay, image position, putting the image needle here using the parallax method. So, this is the image position for the convex lens, okay. And here also this we have put the object needle at 1.5 times approximately that distance from the lens, okay. So, so this is the image for this convex lens. It is the real image and inverted one. Now, what I will do? I will put the concave lens whose focal length we want to measure. So, between the image of this convex lens and the convex lens. So, somewhere here between these two we will put this concave lens. So, concave lens is a diverging lens, right. So, whatever ray was coming and meeting here before this lens, now what will happen? So, this ray will not follow this blue line. So, it will diverge from this path, okay. It will diverge from this path. That means, they will not meet at this position, they will meet away from this position, okay, somewhere here, okay. So, then this will be the basically image, this will be the image for the combination of these two lenses, okay. Now, if you think for this lens, for this concave lens, now for this concave lens basically this is the source, as if this light, this is the object, as if light is coming from here, and then it diverge, and they are forming image here, okay. Okay. So, then we can say this from this lens, this is the object, and this distance is the u, object distance, and the image for this object image is this one. So, this distance is V. Okay. So, basically before, so what we have to do? We have to fix this object needle, and then we have to fix the convex lens, okay, at 1.5 times of the focal length approximately, and then we have to find out the image position. Okay. We have to take the reading of this image position. Okay. Now, we will put the diverging lens, okay, and then we have to find out the image position, okay, and we have to take reading of this image position and the reading of this diverging lens, that is concave lens. Okay. So, actually we need the reading of these three. So, then you can find out U and V, right. So, this is the one set of experiment data you can take, and for these data, so basically generally we take 3 observation to locate the image position and then take average of that one. And then next what we will do, second set of data we will take, just we will change the position of this diverging lens, concave lens by 2 centimeter this side and 2 centimeter other side. Okay. So, 2 more sets of data we will get. Okay. For each position we will find out the image position, right. Then we will note down the position of this diverging lens. It is there already, this noted down, it is there. So, because as long as we are not disturbing these two, so this image which is the object of this converging lens, okay, concave lens. So, this will give us the same reading, okay, only for these 2 different position we will get 2 different image position that we have to note down. Okay. So, basically you need table data for UV and you can find out F. So, number of observation and then position of O means this in this case O I have mentioned this is the object. O means here object position, O1 optical center of the lens. Which lens? This is the convex lens. O2 is the basically this concave lens, and I is the image of this lens, convex lens, and this is the image for the when we are putting this O2. Okay. So, that is why I have I dash. So, that notation I have used here in the table. So, this is the position of the object. I think better to write this object O, okay, object O position, and this is the convex lens position, O1, and then corresponding image position you find out. Now put the concave lens, okay, and note down the position of this concave lens, okay, and then find out the second image, next image position. Okay. So, we note down generally, as I mentioned that actually you can take 3 data and find out the one more column you can find. So, find out the average reading of this second image. Okay. So you will be able to find out for this u and v. Okay. Now second set, as I told, this keep this fixed, convex lens also fixed. So this will be also fixed. Now change this position, this one, whatever, plus minus plus 2, okay, and other set of data you can take minus 2, whatever this earlier reading was there, and corresponding image, this reading you find out, this also you find out. So this way, this is plus 2 minus 2, this now you can find out plus 4 minus 4, this from the original position, okay, plus 4 minus 4, this way you can take other two more reading. So you will get basically u v, either 3 sets of data or 4 or 5 sets of data. You find out, calculate f for each set data, okay, and then average of this f will be your, here another column you can make the mean f, okay, mean f in centimeter, So you find out the mean focal length of the divergent lens, concave lens. Okay. So this is the procedure. So in last class already we have discussed how to find out the image position for a convex lens, and then we will put the diverging lens. So let me show. So here same lens, convex lens we are using, say its focal length is around 10 to 12. So this object needle I put at 0, this one it say it is at say 15, let us keep at 15, okay, and then we found this one is at around 64 something, yeah. So I'll keep the same one, okay, image, I'll keep the same image distance. So this is the image for the convex lens, this is the image for the convex lens, okay. Now I will put, this is the concave lens. We want to measure the focal length of this concave lens, okay. So now I will put this concave lens between the image needle and the convex lens, okay. So let me fix it, and then let me keep at a particular distance, okay. Say I will keep at, it is at 15, say it is at 25, I will keep at 20, no, let me keep at 30, and then plus minus 2, plus minus 4. So that way you can do, or you can start from the say 25, you can start from the 25 and then take reading for say 27, then 29, then 31. So this way you can take 4, 5 reading. So this reading I have to note down, right? This reading I have to note down, because this is the position for the image of the convex lens, but this is the now this is the, as if this is the object position of the convex concave lens, okay. But actually since object is, it is here, so image will form here. So I will note it down this reading. Now this one I do not need to keep it here, right, because that image real image, inverted image, it will form at this position, the reading I have taken. Now, I have to find out the new position of the image, which is basically image for the combination of this lens for this object, or I can say that if this is the position of the object for this diverging lens or concave lens, then that will be the image position of the diverging lens, okay, with respect to this object. Okay. So, after taking reading, if I do not disturb this object needle and the convex lens reading, then just after finding out this image 1, okay, this position 64.4, okay. Now, I do not need to put it here. So, I have to find out the new position of the image, okay. So, I have to see through this lens. So, let me take away, and with bare eye let me check it. It's slightly, yes, I can see. Now basically I can see. So, image will be away from this position, that's the things. Image will be at this position, earlier whatever 64.5. So, now the divergence, it will diverge and it will be away from this position. So, I expect it is, yes. But I am not able to see it. Let me so let me just okay. So, I was trying to set this concave lens, keeping the position of the convex lens of the previous experiment, okay. But what difficulties I feel that when I am putting the concave lens, then I am getting image, faint image, and it was difficult to see the image and remove the parallax error. So, what I have done now, so this is the original position of the object at 0, okay. So, this for concave convex lens, when we are doing experiment, then I kept at 17, and also I told we can keep 15 as well as 19. So, within f and 2f I was it was kept and doing the experiment, okay. And image was beyond the 2f, okay, other side beyond the 2f. So, image distance was far away, and that image was the object for the concave lens, okay. So, since the image distance was far away, So that is why when we are seeing through the concave lens, then since it is from this original object, it is far away. So, intensity is becoming very low, and it was difficult to see that one. So, now I got the suitable position. So, if I keep the convex lens, if I keep the convex lens out of 2f, so it is f is say around 10 for this convex lens. So, if I keep it, so 2f is 20. So, if I keep away from the 20, so I kept it at around 30, okay. And then, so that means the image I will get within f and 2f, okay, within f and 2f. So, if I remove this one, so I have to I will find out the image position, and it will be closer to the lens, it will be closer to the lens, because now object distance is more than 2f. So, image distance will be within f and 2f, okay, this other side. So, now in this way actually image I am getting closer to the than the earlier distance, okay. Earlier it was greater than 2f, it was greater than 2f, okay. Yes, so it is around, I can say, yes. So, it is around say 51.8, okay. So, this the now this is the position of the image needle for this convex lens, for this position, okay, when it is at 30, okay. So, now I will not disturb these two. So, this position I will note down, okay, it is 51.8, right. So, for this position, this will be the image of the, this will be the object of the convex concave lens. So, I put here, okay. So, say I am keeping this one at say around 40, okay. So, now I have to find out the new image position, okay. So, for the position of this, this one is 40, and now this I have to, so now this image, new image will be away from this place. So, it is a diverge. So, this divergence depending on this convex, this lens focal length, it is around 20 concave lens. So, I have to find out the position of this one, yes, yes. It is a small divergence basically, small divergence, okay, small divergence. Yes, more or less this is the position. So, this is 59, okay. So, we have to note down, okay. So, so this is the UV data and F. So, instead of keeping the same data as used for finding out the focal length of the convex lens, so now I have used different position, okay. So, the image will be closer, image will be closer. Then for putting the second lens, I can see that one, okay, because it's a twice diffraction, so that's the intensity will decrease, okay. So now object distance, so it is a 0, convex lens it is at 30, it is as 30, okay. Image distance it was at image distance I forgot something I got around 50, 53 4 probably I got, I forgot, okay. So one has to note down that one, and then now your convex lens position, concave lens position, here it is 40, okay. You have to note down. Now image, new image position, here it is 58.67 or 8, okay. So you have to note down, okay. So then you can find out the observed distance, and then corrected distance means if you have any index error, so note down, okay. Then you can find out the F. So now for different position of the mirror, okay, I will find out the new distance of the image. So keeping this other same, because I am not disturbing this object, original object, as well as the convex lens, okay. So that means image distance, this it will remain same. Now I am just changing the position of this one, different position of this one, and I have to find out the position of the image, new image I dash, okay, and then I can get more sets of data, and then you can calculate the F, find out the. So here what I have learned during doing this experiment, so initially I was trying to keep the lens, convex lens distance within 1.5 times of the focal length, but that for that position this image was distance was more than 2f, okay. So it's a far away. So then I was putting the concave mirror, not mirror, lens, and then the image was going further away. So that means the intensity of the refracted beam was going down, and I was feeling difficulties to see the inverted image and to find out the position of the image. So but if I keep the distance of the convex lens more than 2f, that means that image will come closer, it will come between f and 2f, okay. So that means now this image distance, it is image is, it is a closer, it is closer to the object basically, earlier it was away. So now I will get basically better intensity, and so after putting the concave mirror, concave lens for a particular position, okay, between the convex lens and the image of the convex lens, okay. So I will vary the position of the concave lens at 345 distance, 345 position, and for each position I will find out the new image distance, okay. So and because of divergence, it will go diverge, it will go away from the original image position, which is basically the object of the concave lens. Okay. So, that way one has to take the reading of different sets, find out the mean focal length. Okay. So, here trick is to find out the to remove the parallax. Okay. So, first we have to adjust the distance to coincide the tip of the image needle and the tip of the inverted image. Okay. So, that means you are almost in a position of the your needle is the position of the image position, and then you have to just adjust the slight distance of the image needle to remove the parallax error. Okay. So these the tricks one has to apply. So, this way one can find out the focal length of the convex concave mirror. Convex mirror is easy, concave mirror. Okay. So, so there are another method to find out the focal length of a convex lens. Okay. So, that is called the displacement method. Okay. And I will discuss in next class how to use the displacement method to find out the focal length of a convex lens. So, I will stop here. Thank you.